okay, well they lack markers of lineage commitment. So you might think, okay, well everything that you see here, this large population of cells that you see here, this is actually the lineage positive cells. So then where does this line go? And this is what I was talking about in terms of being consistent with what you do. That is 7.64%. If you just simply drag this and move it very slightly, you can adjust this by almost a whole percentage point. It doesn't look like I did anything. You can't really tell much of a difference between it, but this alters the cell population by a fairly significant amount. So this is what we're saying about being consistent between things, being consistent with where you try and put the gates, how you actually gate it, whether or not you cut and paste them onto your different things, or if you use markers like such as, okay, well I'm just going to gate off of this large subpopulation of cells there. That's what I'm saying, there's no real right. There's lots of different right answers to this. It's not like we all say, oh, well, you didn't put 7.5%. If you get 8.5%, 9, if you get 10%, it's also right as well, because there could be variability between different people. So anyway, so that's what we have in terms of the lineage negative, CD45 positive, which is right here. What is the next thing? What do we gate on next? So what we're going to do is we're going to take this, then we're going to apply this to our next gating strategy in the hierarchy. So what is it? What we talked about before when you said what was the common markers that existed on all the different stem progenitor cells? CD34. So CD34 was one of them. So what we're going to look for is we're going to look for all the cell types that are actually positive for CD34. But then what we're going to do is we're going to start to discriminate between the different subsets of cells. When we discriminate, what is the discriminating marker between your oligopotent progenitor cells, which represent the progenitor cells which are committed to different lineages, versus the multipotent and the stem cells? What is the discriminating marker between them? The one discriminating marker between them? Yeah, correct. CD38. So the next thing we're going to do when we go from our Lin negative CD45 positive cells is we're then going to look at CD34 and CD38. Then what we're going to do is we're essentially going to split this up so that we have our 34 positive, 38 negative subpopulation of cells. Those 34 positive, 38 negative subpopulation of cells, those represent either the hematopoietic stem cells or the multipotent progenitor cells. Then we're also going to take our 34 positive, CD38 positive, and then those cells, the 34 positive, 38 positive, represent all of these what are called the oligopotent, or what we also call the committed progenitors. Does that make sense? Perfect sense. Awesome. So, the next question is, how do we do it? Okay, so we went from our mononuclear cells. From this, we then went to our Lin negative CD45 cells. These are Lin negative CD45 positive cells. Oh, if we double click on this, then what we want to do is look at CD34 and the CD38. The CD34 is Alexa Fluor 700. Alexa Fluor 700, CD34, so it's a 633 laser, 730/45 filler set. Then we also have CD38, which is the Percy P E-fluor 710 here. The E-fluor 710 is 488, 695, 40. With this. So here's what we have. This is CD34 on the bottom. This is CD38 up here. The question is now, where do we draw the gates? This is where it starts to get into the, you need to be able to convince yourself exactly where to draw the gates. Because simply by looking at this, you may be able to kind of say, all right, well, look at this plot. There seems to be a cutoff about here, whereas this represents our CD34 positive cells. But what you would need to do is you actually need to go back to single stained controls, things like that, unstained controls to look to see if that's whether or not that's the case. But then where do you actually draw the CD38 cutoff as well? Again, that involves you going back to the unstained controls, looking at where the profile, where does that exist, and then trying to draw the gates off of that. So, let's go back here to the, the unstained. Here's the, looking at the particular label, which is the 488. So here, this is the unstained controls. You have it here. So the question is then, where do you draw that gate? Simply based upon those unstained controls, you would say that, okay, yes, anything from about here over, like what we said before, anything arminum over here, anything over here, this is positive, and anything from here, above it is positive, below it is negative. If you were to draw the gates, like I say, you would maybe say that this is CD34 positive, CD38 negative. Okay. So you have something like that. Who thinks that's right?
Is the top one, they're both positive?
Yeah, so this is 34 positive. So this is CD34. This is CD38. This is your 34 positive. This is your, sorry, your third, they're all 34 positive, but this represents 38 positive, this represents 38 negatives. Who would have drawn them somewhere slightly differently?
We've drawn it a little bit more this way.
A little bit more this way?
Just because of where
Right.
it is over here.
Over here? Okay. Yeah, I mean, you can. You could take this whole thing, you could shift it over based upon that, if you really want to. If you could convince yourself that I've been a little bit too, I don't know, or less stringent or more stringent with my gate on CD34, you could move this and you could go back. This is why flow cytometry is very much subjective to the person who's doing the analysis of it and the differences between it. So what you have to do, and this is again, I went on and on about this, is you have to be consistent with what it is that you're doing. You have to be able to convince yourself where you're actually going to put these gates. Because in this situation, there's no clear cutoff. It's like that. Now, what else could we do? You could also look at this, I mean, we're using pseudo colors. You could look at other things like contour plots. You get this, density plots, something like that.
So when you're looking at the contour, would you, like, could you put it up against it, but then you wouldn't want to go into the shape?
Right.
Okay.
Right. plots. What the dot plot is doing is it's just showing you, and then yeah, like you say, with this dot plot, maybe you are a little bit too far over here. Maybe according to the dot plot, you would get this and you would actually shift it over so the cutoff's somewhere about here. That's possible as well. However you do it, you have to be consistent. And you have to be able to justify it to yourself and then also to whoever else is going to be looking at your data. When you show the dot plot, what happens is it's going to show you a certain number of dots because, for example, here, the number of dots that's shown, I can't find where the data is right now, but it's only showing you 8,000 dots. You can actually change this number and you can show a different number. You could show even less if you wanted to. Changes it again, completely altogether. The data is still there. There's still, the number of cells behind these different gates. It's just that the data that you're seeing and being represented is that. So that's sometimes why, particularly with the dot plots, it's best to go with a pseudo plot, a pseudo color plot, because it gives you a better representation, because it kind of gives you that heat map as well of it. Okay. So here we've got the CD34, the CD38. What's the next thing that we do? So let's talk about the stem cells and the multipotent progenitor cells. So what we're going to do is we're going to take this CD34 positive, CD38 negative gate, and then we're going to apply the next part of our hierarchy of gating to it, which is what? Is it written down? I forget.
CD90. Oh wait, which population?
Yeah, so we're going to take the 34 negatives. Yeah, so we're going to apply CD90, PE here, then we're going to put CD45RA. The multipotent progenitors are the CD90 negatives, CD45RA, and then the CD90 positives. We're then going to further take this out, and then off of our histogram, we're going to look at CD49F. This is our short-term hematopoietic stem cells, and this represents our long-term hematopoietic stem cells. From this, the CD45RA negative, CD90 RA negative, this represents our multipotent progenitor cells. So this is how the hierarchy is identified. If you want to identify a hematopoietic stem cell, you have to go through the properties of the side scatter, forward scatter. In this hierarchy, gate on Lin negative, 45 positive, 34 positive, CD38 negative, come down here, get the CD90 positive, 45 negative, and then off of CD49F, gate on it. Now, could you have done this in any other way? So the answer is yes. You don't necessarily have to do it in this order, but you do have to be consistent in whichever order you're actually going to do it in. The reason why we do it in this order is because what we gate on first are the things that are common between them, and then kind of split off from it. So this is common, so 45 and Lin is common, 34 is common to them, but then we use CD38 to distinguish between the committed progenitors and the more immature cell types, which are down here. So, if you just double click on the 34 positive, CD38 positive here, and then what we're going to do is we're going to look at CD90 and CD45RA. So the 90 PE is 488, 575, 26. This one